Hello. Um, so continuing on with proofs. So now I'm gonna move on to proof 6, which is the beta distribution. Um, so beta distributions have a probability density function expressed as, I'm gonna sort of write this whole thing down. Alpha plus beta alpha beta x of alpha minus 1, 1 minus x, beta minus 1, 0 x 1. We're going to use the taxicab change of variables to prove that this the distribution is properly normalized, which what that means is x integrated over dx is equal to 1, and we're going to use the definition of gamma function as alpha is equal to 0 infinity x to alpha minus 1 e to the minus x dx. Alright, so first we're going to do the taxicab change of variables. So what the taxicab change of variables are is, I'm going to write down, so we start with some sort of change to x and y, which is equal to y of u v, and in this case we're gonna, so u is expressed as x plus y, and v is y by x plus y. We can multiply these two things together to get uv is equal to y. Substitute this back in, so this gives us u minus uv is equal to x, u 1 minus v is equal to x. This is just nifty to have while we go about doing these things. So substituting these little derived values back up top, we can write down little transformation thing as u 1 minus v uv, that. Alright, so now that we have this, we can find the Jacobian of this transformation phi, which is gonna look like d phi is equal to, so we're gonna differentiate this thing with respect to u, which gives us 1 minus v. Then we're gonna differentiate it with respect to v to get minus u. Then just differentiate the bottom with respect to u to get v, and lastly with respect to v to get u. And finally I'm gonna write down determinant of this thing, phi is equal to u. It's kind of easy to check. Alright, so we will now use this stuff. In this case, we know that u ranges from 0 to infinity, and v would then range from 0 to 1. But I mean, in no case is this gonna exceed 1. Alright, so let's go back to what we were trying to integrate, which was the probability density function. So I'm going to break that into little bits. So tau of alpha beta is equal to 0 to infinity y minus y to the alpha minus 1 e to the minus 1 e to the minus y dy 0 in to infinity x beta minus 1 e to the minus x dx mm, 0 to infinity y to the alpha minus 1 x beta minus 1 e to the minus x plus y dx dy, and this thing is equal to 0 infinity. Just gotta change the bounds 1, put in like the taxi cab coordinates, so alpha minus 1 v is also alpha minus 1 and I don't know what I was doing there. U of beta minus 1 and then 1 minus v beta minus 1 and lastly e to the minus u dv du. And here we're using the fact that we're using the determinant property from what we just figured out here. So I'm gonna again reshuffle all. I'm not gonna reshuffle, but I'm sort of gonna move around all the v terms and the u terms so that they're separated out. So let's go about doing that. 0 to infinity u alpha plus beta minus 1 e to the minus u du 0 1 v alpha minus 1 v beta minus 1 dv, which gives us alpha plus beta integrate from 0 to 1 v alpha minus 1 1 minus v beta minus 1 and dv, which then kind of means I'm gonna sort of divide both sides by tau alpha and tau beta to get alpha plus beta divided by alpha beta 0 1 x alpha minus 1 1 minus x beta minus 1 dx, which is what we sort of kind of started off with, and this would then imply that 1 is equal to 0 1 mu excuse me, the probability density function integrated over dx, and that equals to 1. Thank you.